In this lecture, we're going to take a closer look at skin receptors. And in this illustration here, we see the vast array of structures located within the different layers of the skin. And so the most superficial layer of the skin is referred to as the epidermis, and it's a relatively thin portion of the skin, whereas the thicker dermal layer is a layer that houses the vast majority of sensory neurons that will detect any sort of external contact with the skin and the external world. And there are a number of different types of sensory receptors, including the Pacinian corpuscle, which is what we'll take a closer look at here in this lecture. But we also see what are called bare nerve endings, Meissner's corpuscles, and Merkel disc receptors, as well as hair follicle receptors located at the base of the hair follicle, that if there's any deformation in the hair follicle or any tension placed on the hair follicle, it will trigger the action potentials of this particular receptor. And skin receptors, like most receptors, can be categorized a couple of different ways. And this categorization also applies not just to mechanoreceptors, but to nociceptors and thermoreceptors. Some receptors are referred to as fast adapting, which means that when that neuron is stimulated, it will generate a frequency train of action potentials. But then following the sustained stimulus, that neuron will stop generating that action potential train. So the neuron will adapt very quickly by no longer discharging action potentials. Contrast that with slow adapting receptors, that the neuron will continue to discharge action potentials after an exposure or after a stimulus. So that type of neuron will not adapt as quickly. Another category refers to sensory receptors as being low threshold, which means that from a mechanical perspective in the skin, low threshold receptors are neurons that will be activated at relatively low indentation forces in the range of about half a millinewton, which is a very light type of external contact. Contrast with high threshold receptors, which require a greater mechanical stimulus for these receptors to discharge. And so these are activated at greater mechanical forces. Now, these are not necessarily pain transmitting receptors. However, mechanoreceptors are activated for pain transmission as well. So even though a receptor might be high threshold, it's not necessarily a pain receptor, although that in the event of tissue damage, mechanoreceptors can be activated to transmit that pain information. One particular type of skin receptor that we'll take a closer look at here is called the Pacinian corpuscle. And the Pacinian corpuscle lies deep in the dermis and has some unique characteristics to it. Its measurements put it at about 2 millimeters in length and 1 millimeter in diameter. So in terms of skin receptors, it is a relatively large skin receptor. And what gives it this kind of size is the fact that there are layers of concentric connective tissue, illustrated here on the left in the green. And the Pacinian corpuscle is considered a fast adapting mechanoreceptor, which means that it will stop generating action potentials even with a sustained stimulus. And the mechanism of why the Pacinian corpuscle is a fast adapting receptor is because there's a very thin film of fluid in between these concentric layers. And that viscous fluid will provide a low friction environment, allowing the layers to slide past each other. And the Pacinian corpuscle is particularly sensitive to high frequency stimuli in the range of 200 to 300 hertz. Because of the concentric layers, the Pacinian corpuscle also has what's called a large receptive field. The receptive field refers to the area of skin that the receptor will be activated with the external contact. And to understand the mechanism behind why the Pacinian corpuscle is a fast adapting mechanoreceptor, we start with the upper image here, which shows a mechanoreceptor illustrated in this gray. So what we see here is a bare axon, and that bare axon is going to be stimulated mechanically by this experimental probe. And that experimental probe will cause a physical deformation of the axon. So in the first step here, what we see is the initial pressure of this external probe, which causes a slight change in the shape of the axon, causing it to discharge. And that's what we see here on the bottom tracing in red. So here we see a baseline where there's no bioelectrical activity. The mechanical contact will cause that axon to increase the number of action potentials, forming a train of action potentials. And that's illustrated by this peak here of this tracing. And that results in number 2 here, that initial discharge. But what we see here is that the pressure is sustained. So the probe is still maintained um, on the bare axon, and the neuron is somewhat accommodating here. So although the action potential train frequency and magnitude is decreasing, it's still generating a bioelectrical impulse back towards the central nervous system. So there is some neural accommodation that's taking place. Now, in this final step here, we see that the probe moves upward and it breaks external contact with the sensory neuron or the axon. So with pressure removal, we see that the axon activity returns back to baseline since the external pressure has been removed. Now, when we compare that to the Pacinian corpuscle, which is characterized by a relatively large number of these concentric rings of connective tissue interspersed with a thin film of viscous fluid, we see that we have no contact initially here, so there is no bioelectrical activity. But when the external probe makes contact, you can see that the concentric rings will deform, will bend in, as well as the axon. So that mechanical pressure gets transmitted through the concentric rings, where it will then, the closest layer of connective tissue will apply pressure against the axon. And we see the initial discharge. So with a disturbance of the axon, we see an increase in the action potentials being propagated back to the central nervous system. But because the probe is not in direct contact with the axon itself, the concentric rings will start to slide past each other because of that viscous film of fluid in between each of those concentric layers. As a result, the pressure from the concentric layers of connective tissue on the axon will alleviate. And so we see a much greater degree of neural accommodation than what we saw in the bare axon up on top. And so without that external pressure, we see that the membrane of the axon returns back to its resting baseline, making this entire sensory organ a very fast adapting type of organ. Now, one notable feature here is that when the external probe is removed, so it's moving back upward, we see that there's an axon discharge once again from that removal. And that removal essentially will create a vacuum or a suction, if you will, by pulling it up. And you can see it's illustrated very small here, but the axon will deform in the opposite direction, so it will be stretched as opposed to compressed, as we can see in step number 1 here. And so any physical disturbance of the axon will generate an action potential propagated back to the central nervous system. Now, the Pacinian corpuscle is not the only type of receptor in skin. Another type of receptor are referred to as Ruffini endings, and these are neurons that are found in both hairy and glabrous skin, such as the palm of the hand. And these are classified as slow adapting. So these neurons would continue to discharge action potentials while a stimulus is applied to the area of the skin that would discharge these. Meissner's corpuscles are uniquely found within the fingertips and tend to be fast or rapidly adapting as well. So, with a sustained stimulus, these corpuscles will cease the generation of action potentials. Merkel's discs are found within the epidermal layer and tend to be slow adapting mechanoreceptors. Krauss's end bulbs are a unique type of sensory receptor that is found at the border of dry skin and within mucous membranes around the lips. And the hair follicle receptors have often been described as somewhat of a modified proprioceptor, as it will trigger signals to the central nervous system regarding external contact, but the direction of that external contact as well. So this ends this lecture here on the first part of skin receptors.